So hi, everybody. Thank you for coming. So today's seminar was a bit last minute, so I expected that we wouldn't be too much, but I still think that Claudio can do something quite nice in the short timeline that you had to present something. So today, Claudio will be presenting some work that you did during one of your students' PhD thesis. This is
Brenda's.
So I don't know Brenda, so so I'm looking forward to seeing what you were doing there because I don't know this Brenda, and I hope this will also be interesting for everybody in the room. So this seminar is organized by CORS Montreal, jointly also with GERAD and Cirrelt. So Claudio, the floor is yours.
Thank you, Marilyn. Thank you, everybody, for attending here at GERAD in person and online as well. So what I will present today is the research work made mainly by my former PhD student, Brenda Cobena. So this is, I present the entirety of her PhD project. I want to let you know that the first project of her thesis, I was not involved. So I will present in some work that I was not involved in. But I decided to do it anyway because it tells the full story of Brenda's thesis. Okay, so this is joint work not only with Brenda, but Brenda, she also collaborated with her former PhD advisor, Iván Contreras, and Dr. Luisa Martinez-Merino and Antonio Rodriguez-Chia from Spain. Okay, so the project is about designing a hub, a hub line by considering elastic demands. And the application that we're thinking of is in the design of urban mobility hubs. Okay, so this is the outline of the presentation. I will introduce the problem and motivate the problem. Then I will formally present, the mathematical formulation and what the problem is about. Then the different methods that we designed to address the different variables of the problems that we address, and I will end with some results and conclusions, right? So to understand the need of this project, what we need to understand is that, as the world evolves, transportation is becoming more and more challenging. The use of private cars have increased worldwide. Traveling times have been increasing, and there is an increasing need of better public transit systems, in the cities, right? Right. So if we look at in this picture, where we can observe, it's it's the what we call the urban sprawl, which is how spread the cities are as opposed to dense cities. So, you see a lot, in the US, we see a lot of urban sprawl. So it's very common to have cities that are with very little density, and travel times when you're in the suburbs to get to the city centers, especially when there is a heavy use of private cars, can become very large, So again, there is a need of better and better public transit systems, not only subway lines, but bus rapid transit systems and, public transit systems in more generality. So what this project is about the design of, again, a hub line. You can think of a hub line as a subway line. So how you should design a subway line so as to, shorten travel times and serve as much demand as possible, right? So this is a picture that is telling us, it's a ranking of cities according to, the average travel time per 10 kilometers. So this tells you it's a measure of congestion. So for instance, in, New York is, it's to travel 10 kilometers, people usually need about a half an hour. Montreal, it's a little bit less, 22 minutes, right? But still, important. And I mean, the list this is not an exhaustive list, but just again is to motivate the need for better public transit system. right? So what is a urban mobility hub? And why are we interested in this urban mobility hubs? You have urban mobility hub. You can think of them as intermodal stations where not only one mode of transportation. I mean, where several modes of transportation may interact, right? And it's interesting because it allows for the integration of several public transit systems or different systems. So you not only public transit, you can have a intermodality between trains and private cars, for instance, right? So you can think of a mobility hub something like this. In this project, we're interested, what the application we have in mind is that of designing again a subway line and integrating services along the line so as to better serve the demand that we use the subway line. Think, for instance, if you live in downtown, and let's say you take this, or you live, let's say, no, you're not in downtown. You live in an area where there is no subway line, right? So you have to take your, a bus every morning to let's say, to connect to a subway line, to go to work every single day. If you were given a subway line nearby, that will attract, people like you and other people who will be interested in using that line. But there is more than that. If you get a subway line that's interesting, that will capture demand. But if that subway line is at the subway station is on top of providing the transportation service, also providing more services, you get ATM branches, grocery stores, bike racks to put on your a big C bike rack. All these things will contribute at capturing more demand. Having a grocery store in a subway station doesn't necessarily contribute to lower travel times, but it would contribute at capturing more demand. And in the end, what we want to formalize is the problem it's the problem of maximizing the social benefit. So computed as something that contains reduction in travel times and demand capture. Right? Okay. So in terms of the literature that exists for these problems, we can classify the literature according to two main paradigms. The first is, what is the demand that we observe in how authors have addressed the problem of capturing the demand. Most past studies focus on inelastic demands, either deterministic or stochastic, but exogenous in a certain sense, right? So when we say inelastic, it means that the design of the network does not necessarily contribute to the demands, right? So in this case, we can list these 6 past studies that consider mostly inelastic demands, and our work is the first to address the problem with elastic demands. And also we can classify the past literature in terms of the type of the decisions that are taken, right? So in this sense, we can classify let's say models according to whether they just focus on location decisions, just where to locate stations, but there is also the author that have focused on the problem of designing the entire network, right? So it's two different problems. So either you can focus on location, or a little bit more complex than that. It's location, but with the connections between the different locations, which is more network design type of problem. So our work considers elastic demands, meaning it's endogenous demands that are captured according to the quality of the service that is provided. And what we mean by quality of service is reduction in travel times. Let's say if every day in your daily commute you take, let's say, 30 minutes to get to your final destination, whether you serve, if a subway line that will help you at reducing this in 5 minutes will increase the amount of demand that will, consider the new transportation mode. Instead of 25, it will take 20 minutes. It will capture even more demand, right? And this is what this work is trying to do. On top of the savings in travel times, you also have services as bike racks, as grocery stores, as ATMs, and other services that will also help at capturing demand. So all those things are a key aspect of the modeling of what we did in this work.
Claudio, you prepare the questions now, or like?
If you have questions now, it's okay. For the people in the online, since I don't see them, our Marilyn is taking care of looking. If there's any questions, just write it in the chat. Yes, but feel free to.
Checking your table, you seem to be the first to treat elastic demand. Is that
for this problem, for the hub line location problem? Okay. So there is applications of considering elastic demands for location models. So facility locations with elastic demand that is not new in the literature. I think that have existed like for many years. The literature is still scarce, so there's no much literature on that. But we are the first to consider elastic demands for hub line location models. Okay. Okay. So in terms of the contributions of Brenda's work, I will say that they can be separated in 4 types of contributions. The first is from a modeling perspective. So we are integrating location decisions with network design decisions of designing let's say a subway line, let's say, with demand elasticity that depends on the savings in travel times, but also depends on the quality of the service that is provided. So from a modeling perspective, it's very interesting. From a methodological point of view, I will present in the first model that we came up with to consider the elasticity in demand. You can do that by posing the problem as a mixed integer nonlinear problem. So one of the contributions of Brenda's first work was to give that mixed integer nonlinear formulation, but also provide a linear reformulation of the same model. This is a contribution in the sense that by reformulating the problem as a mixed integer linear problem, much larger problems can be solved, right? The third, let's say, contribution is new methods to scale to even larger problems. So there is a methodological contribution. We do column generation. We do a mix of, we design a matter risk using column generation with local search, right? So with that, we call the scale to solve more realistic problem sizes. And the fourth type of contribution that we have, Brenda, she did a very thorough analysis, in her 3 papers about the impact of the new modeling approach on a realistic case study. So she take data from the city of Montreal, from the origin destination survey in 2012, I think. She took that up. It's public data, right? And so she used that data to design, an analysis to see what we, for instance, they contribute. I mean, the interest in designing, for instance, a subway line on the island of Montreal. So there is she performed that analysis, not only an algorithmic analysis, but I would say mostly a modeling analysis and a sensitivity analysis to understand, the impact of adding more services, having a higher budget for the installation of services. So as opposed to having, for instance, no budget for services. For instance, if you only constructed a hub line, you will capture a certain amount of demand, mostly from having better travel times. But if I give you a budget to construct, again, ATM, grocery stores, to put more infrastructure, we can show that this leads to different designs that are capable of capturing more demand. So these are the main contributions in Brenda's work, right? So now to formalize the problem, the question is, what is a hub line network? You can think of it as again, as a subway line. So you have, where is the, let's say you have customer nodes. It can be, neighborhoods. And if you think of the island of Montreal, it could be the different boroughs in Montreal, right? And then you have potential hub nodes. These are, here you see the hub nodes at the ended up being located, but you could have, 30 potential hub nodes. You need to select some of them. And here we're assuming in the problem that we consider, we're assuming that the number of hubs that are to be located is 6. Right? So it's equal to P. So we have to select P hub nodes, and we have to select P minus 1 R to connect them using a path, right? In such a way that every customer in the, let's say every customer in the network may or not use the subway line. That's a thing interesting. So we are, let's say you can think of it, it's more than just the customers. I would say the customers are commodities. They have origins and destination. So every commodity has a potential origin and a known origin and a known destination, right? So the customers may either use the subway line, right, new one, that would be integrated with the existing infrastructure. So this modeling approach, even if you only see one line, you can think of it as it's integrating this new line with the rest of the public transit system. So every commodity will have the choice to either enter the line or use the existing infrastructure. For instance, if I'm living in a neighborhood and the closest line that the model will construct does not go nearby my home, probably the amount of demand that will be captured for that specific borough will be very low, right? But for neighboring neighborhoods, it will be much higher, right? So in this network, you will have the hub nodes, the one that is let's say the subway line, the demand nodes, but every demand node, it's a node, but commodities are assigned to 2 customer nodes, an origin and a destination, right? You may have, again, direct connections to model the customers that decide not to take the subway line because it's shorter, right? And allocation decisions, right? So this is a problem that we're dealing with, okay? In classical hub line location problems, demand is usually assumed to be exogenous. So again, one of the contributions of Brenda's work is to make demand endogenous to the actual design of the hub line. So understanding how the design of the network affects the demands was one of the motivations to conduct this study, right? So
what does it mean, exogenous?
Exogenous means that it's a parameter in the problem, either deterministic, you can think of it as being deterministic, or could also be stochastic. But that doesn't depend on the design of the network, right? As opposed to endogenous means that the demand will depend on the design, right? So it's not fixed. So what we do is to model this as a mixed integer nonlinear problem with gravity models, right? A gravity model is a model like this, right? Where the demand between I and j, that we call wij, right? We assume that it follows the following formula, which is pi times pj, where this is, let's say, pi and pj are features related to locations I and j. The simplest way of saying this is, could be, population size, the size of the neighborhoods for I and j, right? So how much population lives in I, how much population lives in J, and you could use that as an estimate of the amount of demand that will be linked to, traveling from I to J. And this is divided by Tij at the power of R. This is why this is called a gravity model, right? It depends negatively with, it correlates negatively with the time of travel time between I and J at the power R, where R is, it's a parameter larger than that, right? So, and this is a curve that this is, as travel times increase, you'll see a decrease usually, in demand, right? So, if you provide a service that is very bad in terms of a very high travel times, you can expect that the demand that the service will capture should be low, as opposed to, a better quality of service should lead to a better, demand. So this type of equation captures this type of, model. Okay. So this is an assumption. This is a strong assumption in the sense that this is a very much simplified model. But the why people have used this type of gravity model is because they are capable of capturing to a certain extent, the reaction of demand to quality of service, but also because from a modeling perspective or mathematical optimization perspective, it fits friendly with the optimization model, right? So with this in mind, so we introduce what we call the profit-oriented half-line location problem with elastic demands, and we call it EDHLLP, which is the same HLP, but where demand now is endogenous to the quality of service, right? So this is some of the data that, if you go and look at the papers, so this is the set of commodities. Each commodity has an origin and a destination, a nominal travel time, which is the shortest travel time to go from the origin to link the origin destination in the absence of the line. So this is the current travel time, how much I'm taking today before the hub line exists. And these are all parameters from the model. So I'm not presenting the model here. It's too complex, but what we want to present is what you see in the objective function. So in the objective function, we'll see this. You will see that for every commodity, you will have, this is the gravity model that is here. This is the demand that is captured, right? Is this. This follows this formula, right? Which comes from the gravity model. So this POC, PDC are non-parameters. As again, simplification could be, think of them as, this could be the population size in each of these two neighborhoods, right? But divided by T prime, well, T prime is the new travel time in the presence of the hub line. So this depends on the location decision that we're making, right? This is times RC, where this is just a parameter to account for, the economic benefit associated to the savings, and this is time saving. This is the T prime is the new travel time with the hub line, and T without the prime is the travel time that the customers take before the construction of the hub line. So this is time saving in the presence of the hub line. This is the demand that also depends on the times with the hub line. So there is a very complex model as a mixed integer nonlinear problem that uses this in the objective function, right? But in terms of scalability, it had a lot of scalability issues. Didn't scale too much.
So you wanted to distinguish the revenue from each commodity.
Exactly. So for each commodity, the revenue will be equal to the time saving. So how much time the commodity saves for using the hub line. Time is the amount of demand that is captured. And this is endogenous because, so these two parameters are exogenous. You can compute them offline. But the amount of time that is taken depends on the design that you're constructing. So this is, you know, this is, you can, I mean, in the modeling, in the mixed integer nonlinear problem, you have linking constraints between T prime and the network decisions, you know, the design variables, right? All right. So one important feature of this objective is it's not increasing and convex on T prime. So this is something that we exploit later on for the column generation. So if you go and look at Brenda's first paper, you will see the mixed integer linear problem, which contains this objective function subject to a bunch of constraints. So you can have constraints to compute the right travel times. One thing that is relevant in this modeling is, yes?
Convertible function is not linear, but the constraints are linear or they are often linear?
They're linear, if I'm not mistaken.
Okay,
so, yes.
If you,
yes. From what I remember, the constraints are all linear. Mm-hmm. I think there was some non-linear constraints that were linearized using Markov linearizations, right? And for instance, the connectivity constraint. So in Brenda's first work, so you can write them as software elimination constraints, or you can write them as Miller factor ensembling type of constraint. So in the paper, we present both, and we show that the software elimination constraint work better, right? So yes, mostly the nonlinear nature of the problem is mostly here. And this is how we exploited this attribute to write down a linear model. Right? So we have these two models. There is the nonlinear model, right? That has this, let's say, flow variables, Miller-Tucker ensembling constraint, and they have this mixed integer linear model that we'll explain shortly. So this is the objective function, nonlinear, of the mixed integer nonlinear model. But this is the thing. If you know, if I give you a priori the path that the commodity will take on the network, you can compute the time that it will take. So what we do is we write a path-based formulation where we enumerate all possible paths in the new hub line, right? And for each path, we can compute exactly the time that it takes. So with that in mind, we come up with this objective, which is nonlinear. With G prime, it accounts for the amount of demand that is captured, but it also accounts for the time savings, because when you know the path, the time is fixed, it's known. You can compute it a priori. I mean, if I give you the path, you can compute how much time it will take for the commodity to link its origin with its destination, right? So you use that reasoning to linearize the objective with the added complexity that we no longer have a polynomial number of variables, but an exponential number of them. Yes, Maribel?
But if I look at the hub line, for example, I see it as like a subway line. I would expect as you're adding more and more people, the time that it takes remains stable. Okay. On the other hand, I would expect that if you're attracting more and more people on the subway line,
there is
for example, maybe not on the subway line, but maybe, for example, you're decreasing congestion on the current road network. And so maybe now I know that there's a lot of people that are taking the subway, but for me, maybe it's even faster now to take my car because there's less congestion on the current road network. So clearly you didn't do this here. But what do you think of like this assumption and like how much it would change if you were to try to integrate this aspect?
It's a good question. I think Fabian will be in a better position to answer this type of question. So what I can tell you from my understanding is that, yes, it will make sense to integrate these two things. Now, how much do, let's say, congestion change for private cars in the presence of a subway line? I don't know. It may be important, right? In which case it would make sense to integrate this type of things. So what you're saying is not only consider demands of let's say, of the shorter travel times in the presence of the network as part of your modeling, but the travel times using other modes of transportation also depend on that. It could make sense. I think it makes sense. But now, from a quantitative perspective, how to integrate that, I have no idea.
Maybe you can code that in that part of the gravity model.
So this T will be a one way. I mean, then one simple way of start thinking about it is what you're saying is this T is no longer a parameter, but it's now a variable in your model, or at the parameter that it is. Let's say it's endogenous. You know, it's a decision variable in there of the model. Yeah, it could be. But then it will make the problem even more nonlinear.
Now you can enumerate a lot of things.
Yes.
But I think like if you were to try to think about this, most likely the enumeration that you're doing with column generation probably would.
The thing is, in the column generation, I know the time that it takes with the subway line, right? I know in this part here, I'm not enumerating the entire network. I'm just enumerating the portion that is relevant for one commodity, right? The thing is, what this doesn't have, what it assumes that the nominal time is constant. But the thing is, if you no longer assume that and you think of this time as also depending on the design of the network, I'm not sure that you can compute this G prime using the data that you have. Right? So yeah, I mean, it could be another PhD problem.
I have a question.
Yes.
The parameter R in the denominator, what's the value of this parameter? You know?
This is how much. This is like a price. How much?
Is that the literal R?
Little r. This one. This is the parameter of the gravity model. It tells you basically the speed at which this curve goes down.
Because if it were one, simplest, you may also
if it's one, you will see a linear line here. I think, or no, you will see a 1 divided by t. So we'll see this. But with a higher R parameter, you will see it will go down more quickly.
Okay. Because if it were one, you can formulate the problem as a fractional problem in the t function.
Yes.
And you reformulate it as a linear.
We didn't do that. It could be a way. I mean, it's possible that for specific values of R that the problem may become easier. In our modeling, in what Brenda did in her work, we assumed that R could be anything larger than 1. So we didn't exploit any specific value for it. Right? But it makes sense what you're saying. So with that in mind, so we were capable of modeling this model. And then what we can do is once you know all these paths, basically you can reformulate all your already linear constraints, you know, using this paths now, and everything becomes linear, right? So the only hit here is that this G prime needs to be computed for every single path that you generate, right? So what Brenda did in her first work, they just did exhaustive enumeration of all paths.
They could do it.
And they could do it for a small problem size. So
you have the result.
I don't have the detailed results.
I was just curious about what's the small problem.
She could handle problems with up to 25 nodes and 5 to 7 half nodes. So P equals 5 to 7, right? But not consistently. So this algorithm will fail even for some small instances as well, right? Fail because it will fail at enumerating, right? But they did this because it was already much better than using the mixed integer nonlinear formulation, right? But you can see that these pi variables, they can increase very, very quickly, right? And then that's why so this is when I jumped in Brenda's supervision. So at that time I joined, her project, and we started working on a column generation to handle the mixed integer linear formulation that she had, right? So again, so you can think you have this objective. These things are the problem with the G, to compute G, you need to know the saving. Let's say, and if I give you the path already constructed, you can compute it. But if I'm constructing the path, right? Let's say in a labeling algorithm. Think of a label in a dynamic programming type of method where you start from the origin node, which would be the origin of a commodity. And then you will start adding, using dynamic programming, extensions to the path. The problem is that you can only compute the saving when you reach the final destination. This is at that time that you know how much time it would take, right? So we did that. So this added a little complexity in the dynamic programming, but we were still capable of doing it in a reasonable way. And for that, so we use dynamic programming to generate these paths. So when you do column generation, you divide your problem in a master problem, and a pricing problem. In the master problem, you have a relatively very small number of paths for every commodity, and you generate new paths, again, using this label setting algorithm. So this dynamic programming algorithm is very similar to the ones we use in vehicle routing. You start from, let's say, vehicle routing, you usually start from a depot and you start adding extensions. Here, it wouldn't be the depot, it would be for every commodity, you start from its origin node and you start adding nodes along the path of that commodity, right? You may wonder, what about dominance? The most tricky part in this work was how to handle the nonlinearity part. The thing is, we only know the final cost of the path at the end, because this is when we know the time saving, and we can compute this entire thing here, right? It's only by the end. But the fact that this is convex, positive and convex, helped us at having a dominance role in the dynamic programming algorithm that was friendly with this type of nonlinear objective. So in the end, we did this dynamic programming for the column generation, and it was reasonable in the sense that we were able to solve larger problems, right? So in terms of the type of resources that the column generation or the labeling algorithm considers, you will have travel times. So we define all these resources on top of the cost, right? So you need to know the travel times. You need to know what are the hub parts that are being used. The visited nodes, this is to do cycle elimination type of constraints. And then you need, of course, the dual values from the different constraints in the model, right? So a partial path, you need to we propagate, a partial path when you do a label extension. by recomputing, all these things here, right? And again, probably the most interesting thing that we did here is we exploited the convexity of the nonlinear term to have a dominance rule that wasn't too complex, right? So again, as usually in column generation, we do this label extensions. So we propagate, new paths over and over and over and over again, right? And in the end, we will add the paths. Here we say with positive reduced cost, because we're maximizing profit. And this is good for computing, for solving the linear relaxation of the linear model, right? So the first thing that we try to do at the end of the column generation, for the column generation, we only solve the linear relaxation. So then you could solve the MIP with the genetic columns and see what you get. It was bad. So the column generation as a primary heuristic didn't give good results. Whereas, even for very small instances, we're missing the optimum value.
And here you're just interested in selecting one column.
You mean, no. For every customer, you have one column.
Okay.
Right? And the thing is that the columns need to be consistent. Because, if we have a customer that uses this and this and this path, but there is a customer that lives here and goes there, if we'll take a portion of the path, it should be consistent. So all these customer paths need to be consistent with the design variables, right? But the thing is, so we were getting good bounds. I'd say bounds between 2% and 10% of optimality gap at the root, right? It wasn't too bad. But then as soon as we asked the problem to solve it as a MIP, we were systematically missing the optimal solution. So the column generation alone was not capable of finding good primal solutions. So this is what, in that project as well, this is Brenda's second project, we investigated the combining column generation with local search, right? And this is how we do it. Basically, what we do is the following. We keep at all times a feasible subway line. A feasible subway line is just something it's a line with P hubs. Very simple. So any line with P hubs is feasible, actually. Here we are assuming there is no capacity constraints or anything. So any sequence of P hubs is feasible. So we start with one. Which one you think you use? So we solve the output of the column generation. We solve the MIP, and that gives us a certain solution. That's our first solution. And from that solution, we have two possible operators. We have a swap operator that will basically take, let's say we have the sequence 1, 2, 3. Now this is one possible sequence, in your line. And you could think of the swapping could be just swap two nodes already in the hub line and changing positions. So you could here the 1, 2, you will swap them and you will get 2, 1, 3. Right? The thing is, when you do that operation, the connections from the nodes may not be optimal anymore. As you change the subway line, a customer that was using a certain portion of the subway line, if you change the order in which the nodes are visited, it may no longer be interested. So you need to recompute the savings. So what you do is to evaluate the operator, we need to recompute the travel times for every for every commodity in the network. But this can be done, this is it's a simple calculation. You just follow the line for every customer, you compute for let's say for every potential entrance and exit from the network, for every commodity, you compute its time, you get the best one. And this would give you, the optimal assignment of customers to the subway line. It may happen that in certain cases, a customer that was using the subway line, because of the changes that you did, it's no longer interested, right? And you will observe this. So there's some customer that will be pop in or out from the current solution in the sense that it will enter the network or not use it anymore, right? And the other operator that we use is a replace operator. So basically you take one, let's say one hub in the current line and take it out, replace it by a node that is not a hub node. So for instance, here we were replacing node 4, we're replacing node 1 by node 4. And so the network becomes this, right? And again, in every possible case, the two operators, to evaluate the operators, you need to recompute the time savings for every possible commodity. But it was cheaper. I mean, this was very cheap. This wasn't a bottleneck for the algorithm, right? This is one of the nice features of Brenda's method. And so she realized that not only the solutions are, every time that you find a solution that looks better, I mean, you get a new solution, but you can also get all the path portions for every possible customer that are interesting. So you keep saving basically the columns pi that we had from the MILP formulation. You can extract those from every interesting solution. So every time that she found a better solution, she extracted all the possible pi paths in there. And what we did in the end, so that is step 3 in the method. Execute the local search and generate new paths and new solutions. And then what you do in the end, we resolve the MILP with the new paths generated by the local search. So what happened is the local search may fail at finding the optimal solution or a good solution. But if you keep track of all the paths that you generate, when you do this, and you put these paths back in the restricted master problem and solve it as a mesh, then you get very good solution.
You generate all the, so with the heuristic, you generate all paths that
the heuristic generates solutions. So it searches for full solutions, but every time that a new incumbent appears, you will recompute all the possible paths for every possible commodity in that solution. All the pi's, right? And recompute the all G pi C, right? From the restricted master problem. So by the end, when we have finished the local search, we don't only have a better solution, but we also have a lot of new paths. These new paths are put into the restricted master problem. We resolve the restricted master problem with this new path, and the solution that we get then are much better than the one that we get from solving the step number 2, the RNP, but only with the column generated by the column generation. Even more than this, we realize that the column generation with the exact pricing, yes, it gives us a valid dual bound. But in terms of the solution that it generates, they're not really interested. So our final implementation of this method, we drop the exact pricing. So our column generation is just heuristic in this part here. Step number 1, we just do the heuristic column generation. We keep everything heuristic, and the primary solutions that we find in the end are much better than the ones found by executing the step 1 or 2 here with the exact price. And the third project of Brenda is what happens when we add service, quality of service in the solutions. Well, so what we did is the following. So now in every potential location, we will also consider not only the potential location, for every possible hub node K, we will have this SK, which is the possible a subset of services that can be offered at this location K. Now this is very general in terms of notation. So this can encode, for instance, you could think of this SK as having all possible subsets of services given a budget constraint, or all subset of services given a capacity constraint. Say you have a certain number of square feet to construct your services, and each services occupy a certain area. You could put that as a budget constraint. So this SK here encodes feasible services that can be installed at every possible location. And then we have this. So we assume that the amount of demand that is captured at a certain location, or the demand that is captured for a certain commodity, is sensitive to the services that are present at the entrance of the hub line and the exit, but not for the middle nodes. And it makes sense. When you enter a subway line, you interact with the surroundings of their entrance and with the exit. You don't interact. I mean, you don't get off your trip to, I mean, it's very rare that you will get off to go to the ATM. I mean, it's the amount of demand that is captured is mostly at the beginning and at the end of your trip. So we assume this, right? And this is 2 parameters that are supposed to be known and calibrated in advance. So what we have now, let's say in terms of objective function, it's very similar to the one we had before, but now the amount of demand here, yes, it still follows a gravity model, but now we have this extra quantity FA pi c, which is an attractiveness functions that depends on, this is something that we call alpha c for every commodity. It's just, it's the same as we had before. The attributes of the origin and destination neighborhoods, right? So this doesn't have anything to do with the services that are installed. But we also have these 2 sums here, which is all the services that are installed at the beginning, at the entrance point and the egress points from the network. So we assume that the demand will follow this. Let's say this is a linear regression model that you can calibrate, offline, right? And with this,
it's no longer a gravity model.
It's still a gravity model in the sense that you still have this thing here, which is the time in the current network.
The denominator is no longer
it's not just this. It's this plus the marginal demand that is captured by the different services that are installed in the beginning. So at the entrance to the network and at the egress from the network. So in the previous model, we didn't have this, right? So we didn't have extra services. Now we're assuming that you install a service and this will be able to capture some more demand, and it's given by this term here. Everything else remains the same. So here you have this tau here is basically the time, and this is the time saving, and these are the same path variables. Now the thing is, to model this as a MILP, we took the same MILP model from before, but we realized that a variable now, or let's say a path variable, was no longer only the path. You need to consider the path, but you also need to consider the services at the entrance and the services at the end, right? So the number of paths that you generate are much larger, right? We didn't do any column generation for this, so we replicated, or we adapted our first algorithm, which is brute force, to enumerate variables. So most of the contribution in this work is from the modeling perspective. What does this term bring, I mean, in terms of new decision making, right?
So the constraint is the removal within.
They remain essentially the same, and now you take more constraints of the services. And for instance, one of the new set of constraints that we have is, so for this to make sense, it's convenient to think that you may have a budget for the amount of services you're going to be installing, right? And this is here. So this is new, right? Most of the other things are from the previous work, adaptations, right? So now we did some tests. We use, for the MINLPs, we use Baron to solve them. For the MILPs, we use Simplex with Python. What we observed, for instance, for the first work, when we compare the two formulations, the MINLP and the MILP models, we see that the MINLP model here in the first, you see the gap. So it's much higher gap than the one provided by the linear models. So there was a progress in there. In terms of the computing time as well. So you see that the MINLP models take much more time to solve than the linear models. Right? Now, this is the thing is, remember that we're doing exactly enumeration for the linear models. So you have a question, Anna?
Oh yeah, but if it's an exact reformulation, why you have a difference in the gap?
Because this is the gap at the root node, if I'm not mistaken.
Okay.
So the MINLP give different gaps at the root.
And you also have a time limit?
Yes, there was a time limit. I think it was 2 days. I think. Yes. Right. Then there's this, in this slide, you can see the difference between doing the column generation with local search and the brute force, right? So you can see that I'm not a big fan of this first picture, because it looks like the column generation takes much more time, but it's also because it's capable of handling much more problems. So I think that these times that you see here are just the average in all times. And here, for instance, for the EDHLP doesn't consider timeouts. So that's why you see shorter times here. Right? This is the yellow in the second graph. When you see the yellow line here is the total number of paths that are generated, because this is brute force. You generate all paths. So we see that the column generation generates much less paths. And the thing is, this is a nice feature. The heuristic column generation with local search generates even less paths, but it also achieves much better bounds, primal bounds, the solutions. So the solutions given by the column generation only were not very good, but with heuristic column generation plus local search, we were near optimality all the time. And we're running out of time. So in the end, Brenda did an analysis in all 3 works. She did an analysis, sensitivity analysis, to understand, the impact of of using one or the different methods to construct a subway line in Montreal, right? So what we observe is that by considering the demand elasticity, this is related to her first work, as opposed to not considering demand elasticity. So if you consider a model that doesn't consider demand elasticity, you would construct a network based mostly on cost, right? But will only serve 23% of the demand, where if you include demand elasticity in the model, that amount of demand will be increased. Okay. No, it's not the same network, because the fact of considering demand elasticity makes the entire network shift, right? So this is one of the first conclusions that we had. The next is, I think this is, well, when we applied the column generation with the local search, we were able to consider larger problems, but this was mostly methodological. And this is also interesting. when you compare the problem that includes the quality of service, basically the installation of additional service at every node, you'll see what we observed. This is going to show you. We observed that if with the consideration of the impact of services in the capture of demand, we see that more demand is captured as opposed to not considering that. But the savings in travel times are lower. And it's because the model apparently tends to favor capturing more demand at the expense of slightly higher traveling costs. Right? And this is it. So these are the conclusions. And these are the Brenda's 3 publications. And this is a link to a phishing attempt where I'm going to steal your bank account. Now this is Brenda's Google Scholar. You can go and visit. You can take a picture if you want, if you want me to do. So this is it. Thank you so much for attending.